Welcome to our first section in the machine learning half of this course, linear regression. The linear regression section has the following lectures. We have a theory overview lecture, which is this lecture continued on. Then after that, we'll have a documentation example lecture, where we'll actually walk through the documentation's own example of using linear regression with Python and Spark. Then we have our own custom code example, which is a little bit more of a realistic take on some more realistic data and actually applying linear regression with Python and Spark on that data. At the end, we'll have a consulting project exercise, which we'll discuss in more detail when we get to that lecture. As a quick note, if you've already gone through another course of mine that has machine learning topics, or maybe you've already read about machine learning and linear regression theory in general, you may have already seen this material or already be comfortable with the theory. If you are, feel free to skip the rest of this. The theory of linear regression hasn't changed in a while. Alright. As a suggested reading assignment, I would recommend reading chapters 2 and 3 of An Introduction to Statistical Learning by Gareth James. Let's continue on with the very basics by starting with the history of linear regression. So this entire idea all started in the 1800s with a man named Francis Galton. Galton was studying the relationship between parents and their children. In particular, he investigated the relationship between the heights of fathers and the heights of their sons. What he discovered was that a man's son tended to be roughly as tall as his father. However, this was Galton's breakthrough. It was that a son's height tended to be closer to the overall average height of all people. Let's take a look at an example. Shaquille O'Neal is a basketball player, otherwise known as Shaq, and Shaq is really tall. He's 7 feet 1 inch, or 2.2 meters. If Shaquille O'Neal has a son, chances are that son's going to be pretty tall too. However, Shaq is such an anomaly in his height that there's also a very good chance that his son will not be as tall as Shaq. And it turns out this is the case. So Shaq does have a son, and the son is pretty tall, 6 feet 7 inches, but that's not nearly as tall as his dad at 7 foot 1. And Galton calls this sort of phenomenon regression, as in a father's son's height tends to regress or drift towards the mean or average height. Let's take a really simple example, in fact the simplest example possible, calculating a regression with only 2 data points. So all we're trying to do when we calculate our regression line is draw a line that's as close to every dot as possible. For classic linear regression, or the least squares method, what you're trying to do is only measure the closeness in this up and down direction, or along the y-axis. So in this case, wouldn't it be great if we could apply the same concept to a graph with more than just 2 data points? If we go back a slide, we can see that this particular regression fits the data perfectly. However, if you have more data points, how can we actually do this? Well, to take the same concept, we could take multiple men and their sons' heights and do things like tell a man how tall we expect his son to be before he even has a son. Now, if we look at this plot, we can see for this particular example, we have a perfectly fitted line. We've created a regression line that fits those 2 points perfectly. However, wouldn't it be great if we could apply this same concept to a graph with more than just 2 data points? By doing this, we could take multiple men and their sons' heights and do things like tell a man how tall we expect his son to be before he even has a son. And if we look at this plot, on the x-axis we have a father's height, and on the y-axis we have a son's height, and then various data points. And you can probably already tell just by looking at this plot how a regression line would look on top of it. So our goal with linear regression is to minimize that vertical distance between all the data points and our line. So in determining the best line, we are attempting to minimize the distance between all the points and their distance to our line. Now there's lots of ways to minimize this, and this is basically where that math comes in. Some of these different methods that you may have heard of before are called sum of squared errors, sum of absolute errors, etc. But all these methods have the same general goal of minimizing that distance. So for example, one of the most popular methods is the least squares method. So here we have some blue data points along an x and y axis. Now we try to fit a linear regression to the line. However, the question remains, how do we decide which line is the best fitting one? In order to decide which line fits this data the best, we can use the least squares method, which is fitted by minimizing the sum of squares of the residuals, where the residuals for an observation is the difference between the observation itself, that y value, versus the fitted line. So essentially the residual there are those red lines in this plot. Now let's get an idea of how to implement this idea with PySpark. We'll ease into all of this by checking out the simpler documentation example first. Thanks, and I'll see you in the next lecture where we actually dive straight into this documentation example using the Jupyter Notebook.